Dimension. Dimension in physics has some different meaning, whereas in practical life it sometimes means talent also. You call someone multi-dimensional means simply he is multi-talented. But here dimension means in physics axis also. But here we mean something else. Here dimension refers to powers. What type of powers? Powers are fundamental quantities. What are the dimensions? Dimensions are the powers on fundamental quantities by which they are raised to express a given quantity. When you write the dimensional form of some quantity, then simply you are telling how it depends. You are elaborating the dependence of the given quantity on fundamental quantities like mass, length, and time. You write the dimension of force. If you write this way, it is called dimensional formula. And you put this within rectangular bracket, this will be known as its dimensional form without bracket, and when you put the bracket, this is called dimensional formula. And moreover, if some equation is there, you write both the sides in dimensional form, then it would be known as dimensional equation. Most of the time, dimensional equation is simply used to check the consistency of the given equation. In fact, dimension is used for some very important things. We have sorted them in three categories mainly. Before entering into the detail of those things, we must know what is principle of homogeneity. One very important principle, and that's very fundamental as well. For example, if somebody says add 3 meters and 2 hours, it will be just unbelievable. It will be very uncommon to hear even because we are not used to. Actually, mass is not added with length. Length is not added with time. This is what exactly this principle says. Name itself might be heavier, but the idea it's having behind is very simple one, that process of addition, equation, subtraction is possible only between the quantities which have the same dimension. This is what principle of homogeneity exactly says. On the basis of this principle, you can proceed with many dimensional problems. But here, first of all, we are going to have the detail of first use of dimension, that is to check the accuracy, correctness, or even the consistency of an equation. First of all, we are going to use this one. Now, if it is equation, I told you, so I say T equal to A upon B plus C square D. It looks a bit complex one. But this is very clear, since on one side is T only, then the other side must be having the dimension of time only. This is this principle, so description. On the basis of principle of homogeneity, you can now check the equation here. If it is an equation, left side LT minus 1. Right side, its velocity, final, initial, any velocity, that doesn't matter, initial, final, or in between. Velocity is always velocity and will be having dimension LT minus 1. So this is LT minus 1. Acceleration LT minus 2 into T. This also becomes LT minus 1. So all the three terms you see here in the equation, they are having the same dimension. This addition is also correct on the basis of dimension, and this equation is also correct. This is the simple use that I have elaborated here. Now let's proceed with a bit more, you might say, that is rare in use, lambda h upon mv. That equation becomes relevant in modern physics, but here just to check as an example. You know, lambda is wavelength and length is always L. H is here Planck's constant, that's given on the page. H is Planck's constant, and this will have m L2 t minus 1. This is Planck's constant that has the dimension of angular momentum, and angular momentum too has the same dimension. Then it's a mass and velocity, you know, Lt minus 1, velocity distance upon time. So if you solve them, finally you find here in the right side that's L only. Means left and right both the sides are equal and dimension is correct. Then another example that is d equal to g upon rg. For astronomical objects, the acceleration due to gravity of that very planet or satellite, that's given by the formula. Here, d stands for density of that astronomical object, might be satellite, might be planet, radius of that object, and g capital stands for gravitational constant. If you consider the dimension of left side, that is ml minus 3, mass upon volume. Then on the right side you have acceleration due to gravity, that is Lt minus 2. R radius, you know, L. Capital G, m minus 1 L3. You see, by using this relation you can go ahead and find the dimension of G. But this is always advisable and good for your health to remember some important dimension like gravitational constant, Planck's constant, Boltzmann constant, all that. Hardly universal constants are 6, 7 in number, and if you remember them, it should be at the tips. It will be easier for you to proceed. So I have written it directly. L gets cancelled, T, this gets cancelled, and if you take this whole thing to the numerator, you'll find ml minus 3. Again, this is correct. Now, certain limitations that we come across while dealing with all these uses of dimension is, first of all, when you say some equation is theoretically correct, that must be dimensionally correct. But when you find dimensionally some equation is correct, there's no guarantee whether it is theoretically also correct. Theoretically, it may or may not be correct. One more thing, if some equation is dimensionally incorrect, that equation must be theoretically incorrect.